Hi everyone, today we'll be learning about the pH of salts. In other words, we'll be doing an experiment to determine the pH of a salt solution. So let's get started. We're going to first see methods of measuring the pH. The pH of dilute salt solutions can be measured using either a narrow range of indicators such as litmus or methyl orange, or we can use a pH meter. So you might be using both of them at school, it depends. Salt solutions. So 0.1 moles per liter of solution will be used of each of these salts. So you'll first use ammonium chloride, potassium carbonate, sodium hydrogen carbonate, potassium acetate, sodium hydrogen sulfate, sodium chloride, and ammonium acetate. So with your experiments, first you have to always take care of your accuracy and validity and always address those. So with this, when diluting the acid, use boiled water that was kept in a sealed container to avoid the contamination of oxides from the environment, such as carbon dioxide, that will affect the pH of water. In other words, what you have to be very careful is that sometimes with water, it reacts with the carbon dioxide in the air. Now, when water reacts with carbon dioxide in the air, it forms carbonic acid. Carbonic acid being an acid, it would lower the pH of water. So it is always important when you're going to dilute the acid to use water that is in a sealed container away from any carbon dioxide or any other oxides in the atmosphere. So that way there won't be any contamination, and that way your results will be more valid. Also ensure that all the solutions have the same molarity, in other words the same concentration. So make sure that all the concentrations are the same and the measurements are done at the same temperature, because the temperature affects pH. If you remember what we did, like factors affecting the pH, temperature was one of them, and so was concentration. So you have to make sure that both of them are controlled. Now these are your controlled variables, and it has to be strictly controlled for it to be a valid experiment. Also ensure that the pH meter is recalibrated for acid ranges and basic ranges. So with this, you have to make sure you always recalibrate your pH meter. And to do that, you just simply add your pH meter into a distilled water container and make sure the pH meter is reading 7, and that way you're recalibrating your pH meter. Now with basic salts, they have a pH of greater than 7. So in the proton transfer reaction between a weak acid and water, the hydroxide ions formed, making the solution alkaline. So in other words, we have potassium carbonate. So the carbonate from the potassium carbonate would react with water, and they would form hydroxide ions and hydrogen carbonate. Now why isn't the potassium reacting with water? Remember, potassium is from a strong base. So a strong base, which means when a strong potassium reacts with the hydroxide ions in the water, it would ionize. So in other words, potassium does not react with the water, the potassium ions don't react with the water, but the carbonate does. We also have sodium hydrogen carbonate. Now with sodium hydrogen carbonate, the sodium part comes from our sodium hydroxide. Sodium hydroxide is a strong base, which means that it's not going to react with the water. But our hydrogen carbonate ion is from a weak acid. So because it's from a weak acid, it's going to react with the water to form the hydrogen carbonate, which is carbonic acid, and our hydroxide ions. Now it is these hydroxide ions that's going to make the solution basic. We also have potassium acetate. Now with potassium acetate, same story. We have potassium, which is from potassium hydroxide. Potassium hydroxide is a strong base, but the acetate ion is from acetic acid, or in other words, ethanoate acid. So here we have the ethanoate ion reacting with water, giving us acetic acid and the hydroxide ion. Again, the hydroxide ions are the reason the solution is basic. In other words, a pH greater than 7. Acidic salts. Now, acidic salts have a pH less than 7. So, in the proton transfer reaction between the weak base and water, hydronium ions are formed, making the solution acidic. Looking at some examples, we have ammonium chloride. So, ammonium, the ion, would react with water to form ammonia gas and the hydronium ion. Now, it is the hydronium ion that's making the solution acidic. And just look at this, we have ammonium coming from ammonium hydroxide. Ammonium hydroxide is a weak base, but we have our hydrochloric acid giving us a chloride ion. So hydrochloric acid is a strong acid, that's why it's forming a acidic salt. We have sodium hydrogen sulfate. Now our sodium here is not going to react with water because it's from a strong base, sodium hydroxide. But our hydrogen sulfate, now that's going to react with the water to form a hydronium ion along with a sulfate anion. And it is the hydronium ion here that's going to make it acidic. Looking at neutral salts now, sodium ions and chloride ions do not hydrolyze in water. Now here we're taking the example sodium chloride. Both sodium and chlorine, the ions, come from strong acids and strong bases. So sodium comes from sodium hydroxide while chloride ions come from hydrochloric acid. So both tend not to react with water. So in other words, they don't hydrolyze in water. So ammonium ions and acetate ions do hydrolyze, but the acidity and alkalinity cause almost no change in pH. Because here ammonium ions comes from the weak base ammonium hydroxide. Our acetate ions come from the weak acid, acetic acid. So both would hydrolyze in water. When both hydrolyzes in water, we have the same concentration of hydronium ions to hydroxide ions. Now, if you have equal concentrations of hydronium ions to hydroxide ions, it's going to give a neutral charge or neutral pH, so no change in pH. So that's how neutral salts work. Neutral salts are either made up of strong acids and strong bases or weak acids and weak bases. Now let's just move into some questions. We have question 9 here. It's saying draw a diagram to model an acidic salt such as ammonium chloride. Now when you're doing something like this, you have to always write your equations, see what's actually going inside the beaker, and then draw a diagram. So we'll start off. We'll first see what's actually happening. What's our salt used? Ammonium chloride. So ammonium chloride, in other words, is NH4Cl. Now NH4Cl is going to form ammonium ions and chlorine ions. So there's going to also be water present in the beaker, and that's going to form hydrogen ions and hydroxide ions. So our ammonium ions are going to get attracted to our hydroxide ions here because they're opposite charges, and when they get attracted they form ammonium hydroxide. What do we know about ammonium hydroxide is that it's a weak base, so it's going to only ionize slightly. In other words, this is how our diagram should look like. We're going to have chlorine ions here, those, and then we're going to have hydrogen ions from the water. We're going to have ammonium ions from the solution here, and also we're going to have the acid because it's only slightly ionizing. In other words, it's not going to fully ionize. Because of that reason, we're going to have a higher concentration of hydrogen ions, and because of that reason, there's still going to be acid molecules present. Now moving to question 10. It says to discuss advantages of using models. When it says discuss, you have to provide your own opinion as well. So, models help us to summarize our knowledge, to visualize and understand the concepts involved, and to apply these ideas by making predictions about the acidity of other solutions. In other words, this is a very practical based question. So, this could come up in your prac exams as well as the HSC exam, and it's asking how models are advantages. And mainly in this experiment, it's an advantage because it allowed us to understand the concepts visualize them, and also to apply these ideas and make predictions. So this is why models can be an advantage. Now question 11 asks, discuss the limitations of models. Now again, you have to give your own opinion. Now models are simplifications. In other words, it's not the actual thing, it's a simplified version of what's really happening. So we must be careful that we realize that the chemical species involved are not drawn to scale, and they do not show any information about the number of ions and molecules present in the solution. In other words, the actual size of each ion is not really accurate there. What we draw is a very enlarged scale, while the ion is actually very minute. But they do not show any information about the number of ions. There's going to be millions and millions of ions in a solution, but we only draw 3 or 4 to make it simple and understand it better. So it is very important to know these things before we interpret a model. They also give no idea about the movements of particles and the forces between particles, because especially with two different charged particles, there's going to be attractive forces. With models, you're not able to show that. So that's why there are some limitations with models. And this is how you would go about discussing it. Now let's just review back to what we learned. We learned about how to measure pH of salts. And we discussed how the acidic salts and basic salts and also neutral salts vary in their acidity and basicity.